Welcome and hello. This is a video exercise in HEC HMS. And in this exercise, we are going to be dealing with constant monthly base flow. All right, what I have on my screen here is the HMS documentation page. Down here in the center, we have HMS tutorials and guides. So I'll go ahead and click that. What we're going to be doing is scrolling down to the base flow exercises. And here it is, applying base flow methods in HEC HMS. There's 4 links. The first is an introduction. The second and through fourth is the 3 different exercises. This exercise is going to be this first link for constant monthly base flow. And then the other 2 links are for different types of base flow. So this is about constant monthly base flow. I've clicked on this link, and this URL to this page right here is the URL that's in the description to this video. So go ahead and click that, and you can follow along with us if you'd like. All right, applying constant monthly base flow method. If we scroll down just a little bit here, we have our starting files, and then down below we have the steps one by one that we're going to be following. So the first step is to download these initial files. It's called initial baseflow zip. So just click on that and then click on the download button when that appears. Wait a moment for it to download. Okay, so that's downloaded for me. Go ahead and close that. I have a zip file here over on my desktop, so I'm going to open that up. And what I have is initial baseflow directory and then Puxatawny. Okay, so Puxatawny is the project directory. I'm going to go up one level and then paste that into my project directory where I want it to stay on my computer. So there's that. And then once that's copied, I can just delete the zip file that I downloaded. Okay, I'm going to go ahead and open up this Puxatawny project in HMS. So I've got a new instance of HMS on my screen here. Open, browse, and now navigate to that project, Puxatawny, and then I'm going to select this puxatawny.hms file and select. Okay, it's giving me a quick warning here to say that I'm converting the original source files from 4.11 to version 4.12 because I'm running 4.12. Go ahead and click Convert Project. If you're running a different version than 4.11, you might get the same message. All right, so what I have here is a number of basins. We're going to click on the constant monthly basin here and then expand the basin model map. Also, we have basically a full model that's ready to run, so there's nothing that we need to do per se. The control specification here, it says September 2018. I'm going to go ahead and click on that just to confirm. And sure enough, it's from September 7th through the 23rd of September 2018. We go back to the instructions and scroll down. First, it tells us to open up the project and select that constant monthly basin model, which we've done. The next step is to select the constant monthly simulation and then run it. So what that means is we'll go up to our compute toolbar, select constant monthly, which is right here, and then go ahead and click the run button. Wait a moment for that to run, and it looks like it's completed. Next, let's go ahead and right click on the outlet to the basin and then select view results and then graph. What we have here is a hydrograph of the outlet of the subbasin, where the black line here represents the observed flow data, and then the blue line here is the model results. Clearly, there's some similarity and consistency between these two data sets. There's a peak right here at about September 10th or 11th, and then a second peak about a week later on the 18th. But you can tell there's still some variation between these two data sets that's not very accurate. And by adding some base flow to our model, we may be able to improve the model results based on the observed flow. In addition to looking at the hydrographs, we can also look at this plot here, the summary table. And if we compare the total volume from the computed results of 2.79 inches, that's well off from the 4.49 inches of volume that was observed. So here we have the computed results frame and then the observed flow frame. We can also look at the volume in terms of acre feet by clicking the acre feet radio button here, which I prefer to do, but the instructions look at the volume in inches. So that's what I'll do for this exercise. What's also interesting is comparing the peak discharge, which in the model results was 7650 CFS, and then in the observed data, it was 7810 CFS. So this is a much closer match for peak discharge, but as far as the total volume, we were way off. Let's take a look at that peak discharge one more time. Yeah, so the peak discharge right up here at the top is pretty accurate, but the overall volume of flow over the course of the model simulation was not satisfactory, something we can improve on by adding some base flow. The instructions don't do this, but I kept track of the data itself. So this is my data for the first trial here, where we have the peak discharge, the total runoff comparison, and then the errors. On the far end, I'm also keeping track of Nash, Sutcliffe, and percent bias, and those numbers are coming from the summary table. So if I go back to the summary table, I'm reading those numbers right here. So percent bias, and then Nash Sutcliffe was 0.762. We want Nash Sutcliffe to be 1, ideally. The closer to 1, the better. And then percent bias, we want that to be as close to 0% as possible. All right, well, now it's time to go and add some base flow, some constant base flow. What I'm going to do is click on the subbasin model, either here in the map or up in the Watershed Explorer if I have the Components tab selected. And then down for method, we have base flow method none. So what we're going to do is select constant monthly, this option right here. And by changing that, we now have a base flow tab in our components editor. So go ahead and select that. It brings up a table of data, which is the base flow we want to specify for the 12 different months of the year. Now, this control specification tells us that we're operating in September of 2018. So we could go ahead and type in a constant base flow for all 12 months of the year, but that's really not necessary because we're only dealing with the month of September. So let's go ahead and do that. I'm going to say September here and just say 500. Now, I believe for the model to run, we still need to type in some numbers. So I'm just going to be real simple and just say 0. But that won't affect things because I've tried it both ways. I've tried it as you see it here with only 500 in September, zeros in all other months, and then I've tried it with 500 in every month, and it's the same result for this particular exercise. So with that changed, I'm going to go ahead and click Save. We have our simulation run still selected up here. So I'm going to go ahead and run that again. And then that looks complete. So let's take a peek at the plot first, just because that's cool to look at. And to be honest, the plot looks a lot like it did before. Clearly, there is more base flow here. If I just zoom in here we'll just isolate the first few days. This 500 CFS base flow here is kind of unnatural looking, but makes sense. And then if I zoom out, we have a similar peak flow. It looks like we're overestimating the peak discharge for this time. But altogether, it looks fairly similar. Like there's an underestimation here, overestimation, underestimation, and so on. Okay. So next, let's go ahead and click on the summary table by selecting the subbasin and then click on the summary table. What we see here is, of course, the same data down here for observed flow of 7810, but now we have a much higher peak discharge of 8150 CFS. So now we're quite a bit over. The total discharge of 4.8 inches is now above the 4.4 that was observed. So let's go back to Excel and then advance to our second trial of data. Now we're on the second trial with a constant base flow of 500, but now we've increased the peak discharge to now 340 CFS above what it should be, above the observed data. So with an error of 4.4%. However, our runoff depth of 4.8 inches is now much closer to our target, our observed data of 4.4. So we're 9% over, which is much better than being 36% under. And of course, the last two parameters here I'm getting for Nash Sutcliffe and percent bias. So we definitely improved on Nash Sutcliffe. It's 0.833. And then percent bias, we also improved. It's down to 9.1%. So this is moving closer to 1, and then percent bias is moving closer to 0. So if you're following along in the tutorial, that's sort of it for the instructions. What they tell us is just to use a different base flow method if you want to get your numbers more accurate, and I understand that. But personally, I wanted to run another trial or two to see if I can get these numbers closer. So if we're going to add a third trial with a different constant base flow for September, I think we should make that constant base flow less than 500, seeing that we had an excess of discharge as well as too much runoff volume. So I propose we change it to 400 CFS and see what happens. All right, so let's go back to HMS. I'm going to go back to that base flow tab. And then for September, I'm just going to change the 500 to a 400, click Save, and then go ahead and run the simulation again. I'm going to select the subbasin element and then click the plot icon. So that sort of looks the same as it did before. Let's look at the summary table. This is where we're grabbing all the data. Now we have a discharge volume of 4.4 inches, which is actually perfect. That exactly matches what we want for the total volume. As for the peak flow, we're down a little bit. Now we're at 8050 CFS, and then compare that to 7810 CFS. We're still over, but not quite as much as before. Let's break out the data table and show the results for the third trial here. Again, we have a perfect match of 4.4 inches for our volume, resulting in a 0% error. As for peak discharge, we're approaching 7810, but we didn't quite get down low enough. So instead of being 340 CFS over the target, we're now 240 CFS over the target with an error of 3.1%. The Nash Sutcliffe is up to 0.838, and then the percent bias is down to as low as 0.04%. So we're probably not going to get better as far as percent bias, but we could probably still improve on Nash Sutcliffe, even if it's not using the constant Baseflow method. I'd like to perform one final trial just out of curiosity, and since we got everything set up, and I'd like to just change this constant base flow one more time and see what happens to the numbers. So for the base flow, I propose it be less than 400, even though we're going to incur a little bit of error on the total runoff volume. We're still overestimating on peak discharge. I propose we use a constant base flow of 300 CFS for our fourth and final trial and just see what happens. All right, so I'm going to go back to HMS, click on the base flow tab here in the components editor for the sub-basin element, and then change the 400 to a 300 and click save. Run the simulation one more time. So it's ran, and then we'll go to the results. What we have is a peak discharge of 7950.5. That makes sense. It's linear. We're just dropping it down another 100 CFS. So we're still off the 7810, but it's a little bit closer still. And of course, we only have 3.99 inches of volume. Of course, that's times the area of the subbasin itself. So the actual volume in acre feet is this number here. But 3.99 is far less than the target 4.40, which we achieved in the previous trial. Going back to our Excel, if we see the final results here, I've now highlighted trial 3 because that's our most accurate, but you can see trial 4 is also fairly accurate. We're 140 CFS above the target for peak discharge, but then we're 0.41 below the target volume in inches. So that results in a Nash Sutcliffe and percent bias that's similar to trial 2 here. This 400 CFS of constant base flow is probably the best we can do by just trial and error method with regard to modifying the constant base flow for this model when comparing the peak discharge total runoff volume between the model results and the observed data.